All right, bunch of things to go through today. So I want to talk about some Canvas stuff. I want to talk about PA2. I want to do a little more on stacks. And then we're going to start talking about trees. And we'll be doing trees for the next couple of weeks probably. So we'll try to get started on that today. Any questions up to here? All right, so first announcements. I posted a couple of extra credit opportunities on Canvas. One is for a MESA program, which is going on at Fort Vancouver High School on Mondays. And Nadia is looking for a few volunteers to help out with that. So the students are doing some kind of project where they're using Arduinos. So it's basic C-style programming, helping people connect things, use the software to load stuff in. If you don't have any experience with Arduinos, it will take you about 5 minutes to get the hang of it. And it's a really good thing to have in your toolkit because you can do lots of fun projects with these things. So if you're interested in that, I posted Nadia's email address. Send her an email, CC me on the email so I know that you're doing this. And I'll have her, have a sign-in sheet or something. But you can get 100 points of extra credit in the ODP area. So it's like an extra free ODP. And then the other opportunity is this Friday at 11 o'clock, that's now, in 126, there's a prospective teacher giving a teaching demo. So it'll be a short talk, and we just want some students in the audience to basically listen to the talk, maybe ask questions, and then fill out a really short few question survey of impressions. What were the strong points, the weak points, what did you like about this person, and so on and so forth. Basically, we're trying to find more people to teach courses, and you should be interested in that, right? Because students are the ones that are going to be taking courses from these people, so you get to help be a part of that process of choosing who comes in. So that's 50 points of extra credit, also in the ODP area, and you can do either or both of those opportunities if you like. Since we're in class here at 11, you're welcome to come to the 10 o'clock class that day instead. Don't just blow off the whole class and get your 50 points and then miss the lecture. So
That's this Friday?
That's this Friday. And both of those, oh yeah, Friday's the midterm. So you could take the midterm at 10, and then you could decompress by going to a teaching demo. But don't skip the midterm. Take it early if you want. All right, so those are opportunities. On Canvas, I've also opened up a couple of quizzes. So quiz 3 and 4, these are both due at 5 p.m. on Wednesday. And these will help you with some practice on material for
Where is this extra credit?
it's on Canvas. It should be in 126. It's listed under the ODPs. So quiz 3 and quiz 4, these will help you with the midterm, okay, as review, but they're also graded quizzes. So quiz 3 is all about linked lists, right? All 5 questions worth. But these are short answer, multiple choice questions. So quiz 4 is about hashes, and same thing, 5 questions. So go ahead and please look at those today and either complete them or bring questions tomorrow, okay? Or worst case, Wednesday. Try not to email me at 4:30 Wednesday afternoon and say, I don't know what a hash is. Catch me before then. All right, so I'm not doing any ODPs for the next few days. I'd like you to be working on PA3. I'd like you to do those quizzes, and I'd like you to be getting ready for the midterm. So reviewing what we've been doing so far. So let's talk about PA2. So PA2 looked really good. I think the algorithms are making good sense to everybody, and that's the most important part of this, is understanding this idea of a linked list, having pointers to other nodes, knowing what you need to do to search that structure, to put something in the middle, to remove something, and so on and so forth. So that's awesome. I'm very happy with that. Coding these algorithms, these structures, is kind of a totally separate issue, right? And again, most people seem to have that nailed down perfectly, which is great. That's a question of mechanics, right? It's understanding what this arrow thing is all about. It's understanding when you want to use malloc versus when you don't need to use malloc. It's these mechanics, right? These details of the language, to take the abstract ideas of here's a node, I want to make a new node and point to it, to turn that into actual working C code. And if that's something that you're struggling with, right, just come by and we'll sit down and we'll go through some code, we'll put some stuff on paper, and we'll do that translation between abstract and concrete code. And it's no harder than anything else that you've done in C, it's just different. And once you understand what the arrow means, what the star means, that kind of stuff, then you can be equally proficient with these concepts. And those are the concepts we're going to use the rest of the course. Everything we do with trees and so on, for example, we'll be dealing with pointers. So if you're struggling with that, right, come by either during office hours or shoot me an email and let's arrange an 8 o'clock meeting sometime Monday, Wednesday, or Friday. And we'll just sit down and work out the details. So let me go through some code. And this looks a lot like PA1 did, right? The init function, remember, has a different prototype. It returns a struct node star, but all of these are the same. And the way I wrote this was the same as PA1. I had a process function for parsing and so on and so forth. So the main program has two changes. When you call init, instead of saying init array, you say pointer equals init, right? Because it's returning a pointer to the sentinel. And at the end of this loop, when you exit, I call this new function release, which is freeing memory. Other than that, the main program is the same as PA1. The help message is the same. The init function calls malloc, and I take the value it returns, I save that in this return value, I set its next field to null, and then I return the address of that block. That's the sentinel node. Right? So malloc draws a rectangle on your paper, return value arrow next equals null, puts null in that bottom half. I don't put anything in the data value, I could, and then I return the address of that block. So in my main program, when I say list equals init, what I'm setting list equal to is the address of this malloc's return, right? The address of this new block that was created. So now we see things like this, right? Our add structure takes a struct node star, same as PA1, but this time list is actually just a node sitting somewhere in memory. It's not the beginning of an array. And then previous, I set that to be equal to the sentinel node, right? The header node, so that's a struct node star. And current is previous arrow next. It's what that sentinel is pointing to. Could be null, could be the address of another block. So since I'm adding, I need to create a new block. That's the only time I'm going to call malloc, is when I want to create a node. If I just want to point to a node, like I have cur pointing to whatever previous is pointing to, I don't need a malloc there. In fact, if I do a malloc, I'll probably end up with a memory leak. But I say current is a struct node star. Let's set it equal to whatever previous is pointing to. Okay, down here I'm creating a new block. I set that equal to new. So new is my new node. Check to make sure I'm not out of memory. Save the data field's value to be whatever number I'm inserting. And then our usual while loop, which goes through and looks for a place to insert. So compare current node's data to our number. If it's bigger than our number, I want to insert right before current, right after previous. So previous arrow next says, see what previous is pointing to, find the next field, right? The field called next. Set that equal to new, and new is the address of our new block. So that makes previous point to the new block, and then new, find that block, find the next field, set that equal to current, so my new block points to whatever the current node is. And we're done. Otherwise, this two-step dance, move down the list. So take previous, have it point to our current node, have current point to the node after current. And we iterate until current equals null. And if current equals null, then we have to insert at the end of the list, and that's these two operations. So in pictures, here's what's going on. Let's say this is what our list looks like, and we're trying to insert a 50. And at each point, we've got a previous and a current. Okay, in my mind, when I'm writing this code, here's what I'm thinking. Current is the node I'm checking to see if I should insert right before it. That's the way that I'm thinking about this. There are other ways that you can approach this, but for me, in my mind, this is what's firmly fixed. Current is the node I'm checking to see if I should insert right before that node. Which means that as soon as current is bigger than what I'm inserting, I stop. Right? Current is now pointing to the node I want to insert before, and previous is the prior node, so I want to insert right after previous. In other words, in between previous and current. So that's why I'm checking to see if current's data is bigger than the number I'm inserting. Okay, and in this case it's not, so we do our two steps. We set previous equal to current. We set current to what current's pointing to. Now I'm asking the question, should I insert right before a 30? 30 smaller than 50, the answer is no. Do your two steps to move down, set previous equal to this. Current is current next. Well, current next is going to be null. So current doesn't actually point to a node, it points to null. Okay. Am I checking to see if I should insert right before null? No. Right? Null is not a node. I can't insert before that. So my notion of current has just broken. It's just failed. Right? This tells me I need to start doing something different. So this is what convinces me that my while condition should be current is not null. As soon as current is null, I want to kick out of this while loop. And that brings me down here. Okay, so current is null. I know I want to insert at the end of the list because I ran out of nodes. I can't insert before current, but I can insert after previous. Okay, so at this point in my code, I'm thinking I want to make my new node come after previous. And if that's in my brain, this kind of writes itself. Previous next should be new. And since I know new is the end of the list, new next is null. So this is one of these points that you'll hear me say again and again. Don't memorize this, right? Don't come away believing somehow that when we use linked list, we should always check to see if current is not null. It depends on your interpretation of these variables, what you intend them to be. I'll show you a different version of this where we'll be checking to see if current next is null. Right? So if you have an idea in your mind what you're using these variables for, and you have these pictures and you understand them, you write your code from that. Right? And once you can do that, you can write anything. Trees and tries and balanced trees and red-black trees and all this stuff. It's just going to be like trivial. Okay, you're going to have to learn algorithms, but converting those algorithms into code will become a very sort of automatic process. All right, so print is our standard loop, right? Start with in this case, the node after the sentinel, and if it's not null, print out the data, move down to the next node, and so on. Delete, same thing, current and previous, same meanings as before. If our current node's data is num, then we delete it by saying, have the previous node point to where the current node points. So current has been removed from the list, and then you call free, pass it current, and that releases the memory. So you avoid leaks. And then search, same thing, iterate through the list and check to see if your number matches, and if it does, say we found our number. And then the only new function is release, and this is clearing up all the extra memory. So you said exit, but you had stuff in your list. Okay, the analogy here is you're standing on a stepping stone called the sentinel, and you want to follow this trail of stepping stones, but when you're done, you want all the stepping stones to be gone. You want them to be in your arms. So you're getting rid of all those pieces, right? You cannot get rid of the stone in front of you, because if you do that, you got nowhere to step. You can't get rid of the stone that you're standing on, right? Because you're standing on it. So your only way to do this is take a step forward, go to the next stone, and then reach back, pick up the stone you were just on. Go to the next stone, reach back, pick up the stone you were next on. When you step off the end of the path, pick up that last stone that you were on, and look behind you, there's no stones left, right? You freed them all. So that's what this is doing. So pointer starts off as the sentinel, and I save a reference to it in this variable called free this. I move to the next node, and I free that node that I was just looking at, the free this node. If I'm on the last node of the list, right, free this will be the last node. Pointer will be pointer next, which will be null. I'll free that last node. I'll come up here, pointer's null. I know that I'm done. I kick out of my while loop and I'm finished. So if I call this before I exit, that should clear up my memory leaks. So if you had memory leaks, took off 5 points for it. And finding memory leaks can be tricky, right? The easiest way to deal with those is not to have them in the first place. So how do you do that? Whenever you remove something from the list, make sure you free it and have a good release function at the very end. In a lot of cases, though, well, in some cases, when you run your program under Valgrind, you get all these error messages while it's running, right? Those are hints. Those are telling you that there's something going on that shouldn't be happening. You're either freeing something different from what you should be, which could cause a leak, or you're not initializing something in something that you malloc, which would probably break your program if it was severe. But that can sometimes point you to where you think you're freeing a node, but you're freeing something else instead. So if you want help finding leaks, come by and see me, and we can walk through your code and find those. All right. So other than that, I didn't have a whole lot to say about PA2 other than nice work. Let me show you. Just a slightly different version. So this is all set up the same, but in here, I was thinking of pointer as the next node, as the node before the one that I might want to insert. So I have a while loop while pointer is pointing to something. Right. In other words, there's something after the current node, and if there is, then I set next pointer to whatever that next node is, and I compare that thing's data value, right? But in this case, my while loop is while pointer next is not null, and in my print statement, my while loop is while pointer next is not null, and the same thing in my delete. Right, so what should my while statement look like when I'm doing linked list? Should it be, well, this is not null, or this thing next is not null, or well, this thing next is not null, or what should it be, right? There's no single answer for that. It's up to you, right? This is not magic. This is just code. This is just a rendering of my ideas on how to do these algorithms into C. And whatever algorithm you have in mind will give you a particular set of C code to implement it. All right? But this is not sacred, right? The sacred part is your algorithm. And make sense out of that. Make sure it's something that you understand, and then write code that corresponds to that algorithm. And it doesn't matter if it looks like the code I've got up here or not, right? If it implements your algorithm, it's great. All right, so let me say one more thing about stacks, and then we'll go on to trees. So, did I talk a little about reverse Polish notation on Friday? RPN? So if you have a calculator and you want to do some calculation, you type a 2 plus 3, right? And if you put that in parentheses and you say times 4 plus 5, right? What this means is take 2 and 3 and add those, that's 5. Take 4 and 5 and add them, that's 9. Multiply those, 5 times 9, you should get 45. All right. If we write things like this, we need to use parentheses sometimes, because if we don't have the parentheses, we know that 3 times 4 will get done first, because multiplication takes higher precedence. So we want the additions, lower priority, to happen first. We put them in parentheses. And so you get lots of parentheses in your expressions. So in the early days of calculators, Hewlett-Packard, back in the 70s, were making these pocket calculators. And for whatever reasons, they didn't want to deal with the complexities of parentheses. So when you were trying to do this calculation, you would not say parentheses 2 plus 3. You would enter this in a different form called reverse Polish notation, RPN. And RPN looks like this. You type in one number, you type in a second number, and then you type in what you want to do with those numbers. And normally if you say 5 star 7, it means take 5, multiply by 7. So you have operator, operation, or operand, operation, and then operand. RPN, you put in your 2 operands, and then you say, what do you want to do to those? And this is sometimes called postfix, because the operation comes after the things that you're doing it to. So what would this look like in RPN? You'd have the number 2, and you'd have the number 3, and you'd say add those. And then you'd have the number 4, the number 5, and you'd say add those. And then you'd say take those last 2 things and multiply them. And the last 2 things would be the result of 4 plus 5 and the result of 2 plus 3.
RPN, those pound symbols are
Numbers. Yeah. And so on a calculator, you type in your first number, you hit an enter button. You type your second number, hit enter, and then you hit plus, and the sum would appear. And I'm just doing these as single characters, but there's some way to say, here's my whole number, right? And then operation. And one reason why this is convenient is because it's really easy to evaluate this expression inside a program. Now, evaluating this, you got to know how to deal with parentheses. And if you start nesting your parentheses, these expressions can look really weird to a program that's trying to figure out what should I do next and what should I do with that result. If you put this expression in RPN, it's really easy to evaluate. And it's like a 3-step algorithm. So here's how we can evaluate an expression in this form. So step 1. If it's a number, push it onto the stack. If it's an operator, then pop twice, operate, and push. So anytime we see an operator like plus or star, we're going to pop the stack twice. We're going to take those two things, apply our operation, push the result onto the stack. When you reach the end of your input, your final result is at the top of the stack. So you do one final pop, there's your answer. So let's make a stack. And I'm going to grow the stack in this direction. So the first thing I push is going to go right here at the top. The next thing will come at the next location, and it's going to grow towards the bottom of the page, just because that's convenient. So the top of the stack is actually going to be whatever's at the bottom of the page. So let's just apply this algorithm on this input string. So we get our first number, that's a 2, it's a number, push it on the stack. Go on to the next part of your input, that's a number 3, push that on your stack. Go to the next part of your input, that's a plus, that's an operator. So pop, that gives us a 3, pop again, that gives us a 2. Apply the operation, 2 plus 3, that's a 5. Push the result onto the stack. So now our stack looks like this. It has one thing on it. It's the number 5. Okay, there's 4, that's a number, push it on the stack. There's 5, that's a number, push it on the stack. There's another operator, so what do? Pop the first thing, that's a 5. Pop the second thing, it's a 4. Apply the operation, which is plus. That's a 9, push a 9 onto the stack. Go to the next piece of the input. It's not a number, it's another operator, so pop the top two things from the stack. Well, the first thing is a 9, the second thing is a 5. Apply the operation, 5 times 9 is 45. Push that onto the stack. We're at the end of our input. There should be exactly one thing on the stack. Pop that off. That's your final answer. That's the result of the expression. So this is pretty straightforward to code. If you already have a stack at your disposal, the hardest part is knowing, what's a number and what's an operator, and these can have multiple digits and all that kind of stuff. But the algorithm is really 2 steps. If it's a number, push. If it's an operator, do 2 pops, operate, push the result. So this is sometimes called a stack-based calculator. And it gives you a way, for example, if you're writing an interpreter or something like BC, right? It gives you a way to take an input string and turn it into whatever that expression should evaluate to. So BC is probably doing some kind of stack-based thing internally. Once you get it into RPN, how do you convert from this form into RPN? Well, we can do that with trees. So we'll talk about that in a little bit. Okay, so that's just another application of stacks. Any questions on hashes? I'll go back for a moment. I wanted to mention one other application of a hash, or some of the ideas of hashing. Remember, hashing is built on this idea of a hash function. And the hash function is just this box, right? You put in a key, and you put in an attempt number, a probe number, and you turn the crank, and out pops a number. And that's the index where you're going to store your key. And if something's already in that spot, well, you put the key in the top and you set the attempt number to a 1 instead of 0, and you turn the crank. And you get a different number, hopefully. And if that number's not available, put in the key and an attempt number of 2 and turn the crank, and you keep doing this until either you can't put in any more numbers or you get an answer out that gives you a location that's actually available. And then you store your key there. So this idea of this mysterious blob that you put in some kind of key and you get out some kind of number for a hash, you actually put in also a probe and a temp number. And in general, if you know what came out of this, you can't necessarily go back and figure out what the key was, right? And we don't have to, because we do this for storing, but we also do this for searching. If you want to know, is this particular key in my table, we don't search through the entries, right? We take that key and we take a probe number and we turn the crank and we find out where would that be stored if it's stored in the table. And then we go check that location. So we're always just kind of like transforming our key in that direction. We don't have to go backwards. And this is similar to what comes in when we do password security. Okay, so good password security system, right? Going back at least to the 70s, best practice says you never store passwords on your system. Okay, some places even very recently still do this. And those are bad when they get hacked, because then your password's available to the world. So you don't have a file called password that says this person's password is this, that person's password is that, right? Why? Because you can't assume physical security is an absolute. Somebody can come in and they can go into your building, they can steal the hard drive, and they can take this file out. And you don't want to encrypt these things with some super secret password, right? Because somebody has to know that super secret password to be able to decrypt these user passwords, right? And if that person gets disgruntled and goes off and publishes the password to the world along with the file, right, your passwords are compromised. So you never want to actually store the passwords. So when you change your password on a Unix system and it says, you know, what's your new password, and you say, I like unicorns, that password is never stored anywhere in the system. There's no file that contains the string, I like unicorns. Okay, that's really important. So how do you do password authentication if you don't store the password? You use something like a hash function. And so you have some sort of process that takes a password and it turns it into gibberish. And it's this gibberish that you store in a password file. Yeah?
Does that mean that there's a good chance that there's random gibberish passwords that would...
Yep. Yeah. And when I was first studying this, I was using an operating system called VMS. And it turned out that if you had like a 9-character password, you could add 1 to the first letter, subtract 1 from the 9th letter, and that would also get you logged in. Or you could add 3 and subtract 3, because it was really just breaking everything into chunks of 8, adding them together, and then it was doing something really fancy. But it was really easy to find like different passwords that would work for that. Cool observation. So yeah, you take your password, you turn it into gibberish. So what happens when somebody wants to log in? It says enter your password. They type in their password, goes through the same function, turns it into gibberish. It compares their gibberish to the stored gibberish. If it's the same, then you say, I guess this person knows the password. This only works if there's no way to go from here back to an original password or an equivalent password. So this has to be like a one-way function. And there are presumably one-way functions out there that take your input and turn it into something, but there's no reasonable way to produce another something that will give you that same output. And now the security of your system is based on whether or not that's actually a one-way function. So the password file on Unix used to have, instead of this X, it actually had the encrypted password stored. And it was a publicly readable file, right? Everybody had access to this. And so you could authenticate users yourself, and the algorithm was totally published. So you could take somebody's password, something that they said was their password, you could run it through this encryption, you could compare it to this second field in this file and see if they had the correct password or not. So now they don't store the passwords in here anymore. It's a more sophisticated system. But for a long time, the encrypted passwords were totally readable. And Now that's kind of a brute force vulnerability, but it worked well for a long time. All right, so let's talk about trees. So remember how we got to where we are, right? We started off with this idea of storing numbers, and if we store them in an array, that's fine, it's easy to insert. It's a little expensive to delete because we want to move things up, but it's really hard to search, because to search an array for a number, you just have to check each element. That's an order n operation. So we said, well, let's sort our elements, and now we can do the following. If I want to search for a number, I can start with the middle of this array, and I can say, is this my number? No. Is my number bigger or smaller than this? If my number is bigger than 15, I can ignore the first half of my array. And I can say, I'm just going to check this smaller array. And we do the same thing. Let's compare our number to the middle. If our number is smaller than that, I can discount this half of that subarray. I only have to check this much smaller array. And so each operation we do basically cuts our problem size in half. So if we start with 1,000,000 numbers, it takes us 20 of these halving operations to get down to an array of one number. And that's either our number or we didn't find our number. So this is a log n operation, right? Log base 2 of n is how many steps it takes. So 1,000,000 numbers goes down to 20 steps. 1,000,000,000 is 30 steps. It takes 10 more steps. The problem with this is, since our data is sorted, inserts became really expensive, because if I want to put in the number 3, it's got to go right here, and I've got to move everything down in order to make list for that 3. So that led us to talk about lists, where these things are not stored in sequential locations in memory. They can be stored anywhere in memory. And to find each piece, we have a pointer from the previous piece, and now if we want to insert, we just point to our new node, have the new node point to where it should go. And so that's our linked list that we've been playing with for 4 weeks now. And that's great, but when we have a linked list, we've lost the ability to say, let's start with the middle node and see if we're bigger or smaller. The only way we can search a linked list right now is to start at the beginning and just check each node to order n. Right, so we tackled insert and delete. Those are order 1 now, but search is still order n. So we're going to modify our linked list as follows. I don't think those are the same numbers, but that's okay. We're going to start off, instead of a sentinel that points to the first node, we're going to have a pointer to this middle node. And we're not going to have a sentinel node anymore. Okay, we're just going to have a pointer to this first node, and we're going to call that pointer the root. And so we can look at the root node's data, and we can say, is our number equal, bigger, or less than that? And let's say our number is bigger than the root node's data. We don't have to deal with anything over here. We only have to check this smaller list to see if it contains our number. Well, ideally, we'd like to begin with the middle node of that. So we also want something that points to the middle of this list. And if our number was smaller than 15, we'd like something that points to the middle of the smaller list. Well, I'm going to store the pointer to the middle of the whole list in just a struct node star called root. But where should I store the pointer to this and the pointer to that? I could have, root 2 and root 3, but as my tree grows, I'm going to need more and more variables. So I'm going to do something like what we did with our linked list. I'm going to store those pointers as part of this node. So my node is going to have 2 pointers. A pointer to the middle of the list on the left and a pointer to the middle of the list on the right. And when I look at this, if my number is bigger than 35, I want to go to the middle of the list on the right of that, or the left. And same thing, I'm going to store a pair of pointers to those points. And if there was more stuff over here, my 42 would have 2 pointers, one to the middle of the left sublist, one to the middle of the right. And so this is what we're going to call a tree. And I'm going to draw it in a slightly different form. So here's my 15, that's the root. I want a pointer to the left, which goes down to 5. And I want a pointer to the right, which goes to 35. My 5 should have a pointer to the left, which goes to 1, a pointer to the right, which goes to 10. My 35 should come to the left, 27, and to the right, 42. It's the same information, but it's written in a different form. And I don't need to label the root because the root is always the thing sitting up there at the top with nothing pointing to it. It's the beginning of the whole tree. So this is a tree. Because each node has only 2 children, or maybe 1 child or no children, right? At the most 2 things coming off of it, this is actually a binary tree. And because I'm storing information that's sorted, this is actually a binary search tree. So a BST. And mostly we'll be talking about binary search trees. And you can think of it as a kind of quirky linked list, but it's its own structure, right? Because each node has 2 pointers. And it has a number of useful properties. For example, if I look at the root, everything to the left is smaller than that. Everything to the right is bigger. And we know that's true if we go back to this picture of it, right? My pointer to the right is to the midpoint of this list on the right, but everything to the right of this must be bigger. So certainly everything in that section is going to be bigger, and same thing on the left is smaller. And this whole thing is a tree, but if we go to the left of the root, this little thing here is also a tree. It's got a root of 5, and it's got a 1 and a 10 hanging off it. And this thing on the right is also a tree. It's got a root of 35, and it's got things hanging off of it. So let me give you some terminology definitions. So root is basically the top node. And here I'm thinking about kind of an arbitrary tree. So this is a perfectly fine binary search tree. It looks weird, maybe, but this comes from a list where we have those arrows going to the midway points on each side. And so the root of this tree is 40. Okay, it's the node sitting at top. And I'm always going to draw these things in this way where they kind of branch out as you go from top to bottom. So it's an upside down tree, right? The root is sitting up in the sky and it's branching out as we go down. So we can talk about nodes in terms of being parents or children. So if we have an arrangement like this node here is considered the parent of that node, and that node is considered a child of the parent node. So 20 is a child of 40. 60 is also a child of 40. 20 is also a parent of 10 and 30. Right? And 10 is a parent of 8. 8's a child of 10. Eventually we'll talk about grandchildren and aunts and uncles. But that'll be towards the end of the course. So we'll use this ancestry model sometimes as a way to discuss things, particular nodes in this tree. Now, a node that has no children is called a leaf node. So 7 is a leaf node, 9 is a leaf node, 30, 55, 77, those are all leaves. And not every node has 2 children. Leaves have no children. This 6 over here has 1 child. I don't usually draw the null pointers. Technically, the pointer to the left is null, but I'm just not going to draw it on the picture. It's going to make it really complicated if we do. So if we don't have a line coming off in the direction, it means that pointer is null. Okay, so we can talk about the depth of a node. And that's the number of steps from the root to the node. So for example, this node 8, how many steps does it take to get from the root to the 8? Well, start at the root, we have to go 1, 2, 3 steps. So this has a depth of 3. The 10, on the other hand, has a depth of 2, because from the 40 we have to go 1, 2 steps. The 30 also has a depth of 2. We come 1, 2 steps to get to the 30, as does the 55, as does the 72. So depth is really kind of, you know, how far down you are in this tree-like structure. So this 9 has a depth of 4, the 6 has a depth of 4, the 7 has a depth of 5. This also has a depth of 3. The 80 has a depth of 4, and the 77 has a depth of 5. What's the depth of the root? 0. Because we don't have to follow any steps to get from the root to the root. Well, once we know what the depth of each node is, we can define the height of the tree. And that's just the maximum depth of any node. So find the depth of all your nodes, whatever the maximum is, that's the height of the tree. In this case, the tree has a height of 5, because the deepest nodes have a depth of 5. So if you have a node that only has a root, what's the height of that tree? Right? The only node is the root. It has a depth of 0, so the height of the tree is equal to 0. Okay, so here's one odd case. Suppose you have a tree which is null, has no nodes, it does not even have a root. -1. Perfect. We're going to define the height of this tree to be -1. And there's no real logic behind that, because there is no node of depth -1. There are no nodes at all in this tree. But if we make the height -1, things that we're going to do in a few days will work beautifully. So it's a really convenient definition. It's like 0 factorial equals 1. Why? Because it makes things work out nicely. All right, so a null tree will have a height of 1. And I didn't say this, but we'll talk about left and right as far as directions of moving through this tree. All right, so we will start talking about traversing trees tomorrow, how we go through a tree and pull information out of it, why we want to do that, and then we'll start looking at coding and then some other aspects of tree-like structures. All right, so we'll start that tomorrow.